All right, welcome. Ready to get started? Our last class, basically.
We got faith.
Wait, I was like, what?
And that was priceless, man. I like that face. Yes, she was happy.
So anyway, a couple of announcements. First about the final exam. We're actually going to do the final exam on Blackboard. You won't have to come to class.
Okay, that's what I said for me.
Okay, so it's good for you, but it's not good for everyone else. And in addition to that, I'll open up the exam on Sunday. Like this coming Sunday at midnight.
After the Super Bowl.
And you'll need to complete it by the end of the day on Wednesday. It's a 3-hour exam, so sometime Sunday, Monday, Tuesday, or Wednesday, complete the exam.
Is it one sit down or can you save and go back?
Midnight
It's one sit down.
on Sunday, right?
It's exactly like the quizzes. And it's quiz questions. It's just the same quiz questions, and actually in a minute I'm going to tell you which questions are on the exam. But it's just the pretty much the quiz questions that you took for each quiz with just different numbers. Let's put in different numbers. What else?
How many questions do you have?
8 questions.
Oh, 8?
8, is that, are you surprised, is that too low or too high?
I don't know.
You're surprised though,
In one
right?
question, right? It depends how many steps in one question. Exactly.
Well, you've got 3 hours.
3 hours?
Yeah, it was 12.8.
Oh, it's on here. Oh, okay, well, that's better.
Sunday after midnight. So you have until Wednesday.
It's all a matter of printing out all of them.
It's like putting all your bread,
Alright, so first question is a Z-stat in between question. You remember that in between Evander Holyfield's height and Manny Pacquiao's height, what's the probability the next guy who walks by will be in between heights? And remember we had a driving distance question. What's the probability a random person you're talking to drives in between this much and this much? The second question is a confidence interval for a mean. You remember what to do if you don't know the population standard deviation? Does everyone remember what to do if you don't know the population standard deviation and you're trying to calculate a confidence interval for a mean? Alright, so hopefully you'll figure that out before you start. You can watch it on video.
When you do not know the standard deviation.
The third question is a proportion confidence interval. Proportion confidence interval. Alright, the fourth question is a proportion difference confidence interval. The fifth question is a hypothesis test for a mean. Hypothesis test for a mean. Let's see. The sixth question is a hypothesis test for the slope of a regression equation. So we got a sample regression line and we got a sample slope. Of course, you do a hypothesis test to determine whether or not that slope is statistically different from 0. The seventh question is a dummy variable question. And the eighth question is a chi-square question, which you will learn tonight. And so you'll learn chi-square tonight, and you will, take the quiz on chi-square. And then you will, and then you will adjust based on what you learned from the quiz, because let's see, the quiz is going to be, or the exam, like I mentioned, is going to be exactly like the quiz questions. So it'll be the quiz question you take on chi-square, but with different numbers, slight alterations to the problem. Any questions?
No extra credit, no bonus?
There is no extra credit. Yes,
When are you
Karen.
gonna put the video up?
What's that?
You gonna put the video up tonight?
Yeah, maybe tomorrow. Yeah.
I didn't write them down, I just wanted, I
Okay.
watched it in
Just trying to absorb it. That's good. This will be it.
Yeah.
No Excel?
You can use Excel.
No, but I mean, there's no Excel, like the homework,
Oh
Excel
yeah.
problems, no.
Now, hopefully the Excel helped you with the homework problems, or helped you understand, or helped you.
Just fit it in, the numbers just fit it in, and it did everything itself.
Right. So hopefully that's what the Excel homework helped you with, but you won't have any Excel challenges on the exam. What else? So tonight, as I mentioned, we'll learn chi-square, which is fairly easy. It won't take us that long. After we go over the chi-square material, I want to give you a minute to fill out your course evaluation for this class. I'll show you how to bring it up on Blackboard, and I'll leave the room, let you fill out the course evaluation and take a quick break. And then we'll come back after that, or I'll come back after that, and I want to show you an Excel method for doing chi-square. You may notice that the Excel problems for this week are optional, because I don't think they really help you that much. I think they're more confusing for just the chi-square material. The actual textbook Excel problems I don't think help you much. So I'll show you the way I would recommend doing it. And then after that, I'll be around if you have any questions. I'm gonna catch up on anything. Any questions?
Yes,
Yes.
for the last homework, that's what you're gonna teach us today, how to do the optional part.
The
You just mentioned, I'm sorry.
the last homework, which last homework?
The last two
Yeah, read it.
questions for the homework, they're a little confusing.
Oh, for the Excel homework?
Yes, I believe that that's what you're gonna teach us.
No, we're gonna go over chi-square tonight. And so if you did Excel homework from last week, that was multiple regression. And your feedback is that got a little complicated?
The last optional question, the last three, it's confusing, that's all.
All right, I will note that. What did you all think about the multiple regression Excel homework that was due today?
Yeah, that third exercise was
Yeah, it was a little.
a pain in the ass.
Pain in the ass?
Yeah.
Did anyone like it?
It's just time consuming.
Time consuming?
Is that what chapter 12?
Which
Yeah.
one was it, like, no, it's all right, I
Actually,
didn't have a problem with it.
good. Carol liked it?
Okay.
Compared to past Excel problems.
Okay. Well, actually, I'm glad you brought that up, Adamus, because I'm actually next quarter, I think I'm going to cut out what was the second hypothesis test class. I think I'm just gonna cut that out and spend an extra day on regression analysis, doing those, okay, excellent, doing those things that got a little tricky. So thank you for bringing that up. Alright, so let's do chi-square.
Professor,
Yes.
so we have to do quiz number 9 and the exam.
Yes. Do quiz number 9, do the exam, and do anything else that you haven't done up until this point. Any Excel problems that you haven't done, any past quizzes you haven't done, please have it all done by Wednesday. Because if it's not done by Wednesday, I'll actually go through and I'll put a 0 in for it. It may not look like it's hurting your grade now because you just haven't taken it yet, but do it and you'll be fine. Excel, just do like you do, make an effort, you'll get 5 out of 5 probably. And if you were passed on any quizzes, unfortunately, you didn't get the benefit of taking it at the time, but still take it now. just take it in, yeah, oh, great, yes.
So you have quiz 9, it's due February 7th, so is that's not the final, this is just the
It's
quiz?
not the final, so February 7th is Wednesday, right?
Yes,
Yeah, so Wednesday at like 11:59? Yeah,
no, it says Wednesday, 6:30.
okay, 6:30, all right. So yeah,
But
the
I'm
quiz is
asking-
due at 6:30, the exam is due 11:59.
All right, so there's gonna be 2 things due that day, the quiz
Yeah.
and,
But you can do them both starting on Sunday. In fact, you can do the quiz starting now if you want.
yeah, okay.
And you'll be comfortable, I hope, to start the quiz at the end of class tonight. We'll go over the chi-square material, I'll show you the Excel tricks. You'll be able to knock that out of the way. You'll be able to see the answers like you can with all of the quizzes. Everyone's been looking at the answers to past quizzes. And especially I would look at the answers to past quizzes that I just listed. Right. Alright, so chi-square, there are 2 things that we're going to take away from chi-square. One is the chi-square test for proportion differences. So are 2 population proportions different? Are 3 population proportions, are they different or are all 3 the same? Second thing we'll take away is the chi-square test for independence. Are 2 variables independent of each other? Or are they dependent on each other? So what do I mean by independence or dependence? If I said I have 2 variables, one is your shoe size, and the other is your grade in statistics class, do you think those 2 variables are independent or dependent? Independent, sharp class. They're independent, they have nothing to do with each other. So if we categorize people by shoe size, the proportions of A's and B's would all be the same. For the people who have small feet and big feet, they would have the same proportion of A's, same proportion of B's. On the other hand, how about hours of study time and statistics grade? Do you think those are independent or dependent? Dependent, yes. Your grade depends on hours of study time. So if we categorize people who study a lot and people who study a little bit, the proportion of A's in those 2 groups would be different. So different proportions, dependent. So those are the 2 things. Chi-squared test for proportion differences, chi-squared test for dependence or independence. I'm going to start off with an example which will bring this into context for us. Suppose you were to take a survey on class offerings among Manhattan, Dobbs-Ferry, Bronx MBA students at Mercy College. And you were to ask them this question. Does the Mercy College MBA program provide an adequate selection of course offerings? You take a simple random sample of 100 students in Manhattan, 100 students in Dobbs-Ferry, 100 students in the Bronx. The percentage of people who say yes is this number in Manhattan, this number in Dobbs-Ferry, this number in the Bronx. So, this is a sample. This is not every single student. We now have a sample proportion. So what do we want once we get a sample proportion? What is our goal in life at that point? We said, what's that?
Define the population proportion.
Define the population proportion, all right? That's the single, all-consuming thought on your mind at that point, right? I now have a sample proportion, but that's just based on a sample of 100 students at each campus. I really wonder what the true population proportion is. So, are my sample proportions different? Yes, they're different, okay? This is 89, this is 77, this is 61, that's different. Question for you. Are the true population proportions of this population, and this population, are those different?
Wait, say that again?
are the true population proportion of Manhattan students, true population proportion of Dobbs Ferry students, true population proportion of Bronx students, are those different?
No.
Alright, so some people say yes, some people say no.
I would say
Probably
no,
not,
but
yeah.
I-
But then
I
again,
think
they
don't
don't
take-
It took 100 from
Murphy
each campus.
itself, but different
So
campus.
that's why I was saying, no, it's 100 from each campus.
Each campus, what do you like or dislike about that 100?
Well, it could be
I'm sorry, I have to say
no,
yes.
low numbers on one side and could be high numbers on the other side, we don't know yet.
We don't know, yes.
Maybe Manhattan College has more, students than Bronx and the Ferry. Ferry has the least, and Bronx probably second, because population here is bigger than up there and down there.
Okay, okay.
So,
The real underlying thing is, this is a sample, and we don't know for sure what the true population proportion is. But we could guess. We have evidence that the true population proportions are different, because the sample proportions are different. But are they different enough for us to say, yes, the true population proportions are different? Are the three true population proportions different? We want to know the answer to that question. Let's do the chi-square test for differences in population proportions. Let's do that. Second question I want to ask when I look at these sample data. Are student opinion and location independent in the true population? What does that mean? Student opinion and location independent? What does that mean?
Which campus? Their based upon where they live.
No, based upon the location of the campus. Does the opinion or the answer provided in the survey, does it depend on where they go to school, which campus? Whether
Okay,
that's
so we have
independent?
three populations. We have a population of students who say they're Manhattan students. I know in real life you intermingle, right? Manhattan, Dobbs Ferry. You may not identify yourselves as a Manhattan student or a Bronx student. We're just assuming for the purposes of this example, there are students who say, my main location is the Bronx, my main location is Dobbs Ferry, my main location is Manhattan. So we have three populations. Manhattan students, Dobbs Ferry students, Bronx students. And they have opinions. The Bronx students have an opinion, the Manhattan students have an opinion, the Dobbs Ferry students have an opinion. Are student opinion and location independent? What do I mean by that?
Do they correlate with one another?
Okay, can you?
Is it that they don't affect each other?
Yes, that's right. Independence means they don't affect one another. So it doesn't matter which if they're independent, it doesn't matter which campus is your home base, that does not affect your opinion on this matter. Does the Mercy College MBA program provide an adequate selection of course offerings? If they're independent, Manhattan students, Dobbs Ferry students, Bronx students all say the same thing. If they're independent. What if they are dependent?
That means their answer would be subject to where the campus is.
Yes. Their answer would be subject to where their campus is. So you would have a different opinion based on their campus. And it looks like they do, right?
Mhm.
It looks like the Bronx students say no. Looks like the Manhattan students say yes. And you could imagine a scenario for this. Most of the course offerings, or more of the course offerings, are in Manhattan. Fewer are in the Bronx. So of course the Manhattan students are more likely to say, yes, you provide an adequate course offering. So it looks like they are dependent. Location is, or opinion is dependent on location. And how we tell that is that the true population proportions are different. And if that sounds familiar to the first question I asked, are the three true population proportions different? It's because it is. How do we tell if opinion and location are independent? Well, we look at what the true population proportions are. If they are different, then in fact, the two variables are dependent. If they are the same, if all of these were the same, the true population proportion here, here, and here, then these factors would have nothing to do with each other, they would be independent.
Would they have to be exactly the same, Professor? Would they have to be the
They
exact same?
do, they do have to be exactly the same. So you're saying if it's just like one fraction difference? From our perspective, we will never know exactly the true population proportion. We'll say if it's close enough where we can't tell a difference statistically, we'll say that they're the same. Good question, I have thought about that though. So if they're not like exactly the same, you technically have to say they're always dependent. Okay, we're feeling okay with this? Well, this is exactly what we'll talk about for the next hour, so if you're feeling a little shaky, we'll add some clarity. So we'll do these two tests, chi-square test for proportion differences, chi-square test for independence. And as I mentioned, they're the same thing. All right, the answer to this question is provided by this, so they're done exactly the same way. Yes, Ron?
This works with just one sample, you don't need a sampling distribution?
So yeah, we'll take, with a sampling distribution, it gives us a confidence interval about our sample, and it's the same thing. So this is a sample based on 100 students. So how can we make inferences about a sample based on 100 students? Well, it has to do with what we know about that theoretical sampling distribution of the sample mean. Same concept is underlying this.
Okay.
You'll just, yeah, it is. All right. So, and then we will just talk about the chi-square goodness of fit test. We won't do the calculations for that because it's slightly different. I think we just only need one chi-square test to really get a sense of it. But the goodness of fit test is if I were to say that the true population proportions are some specific numbers, say 94 in Manhattan, 83 in Dobbs Ferry, 68% in the Bronx. If I were to say that that's what the true population proportion is, all right, that's different than my sample data. So does this sample data prove my hypothesis wrong? All right, so this is what I say the true population proportions are. I get different sample data. Is it different enough for me to say my assumption is wrong? Well, that's the chi-square goodness of fit test. When we get to that, I'll pretty much just repeat exactly what I just said, and that's all we'll do for chi-square goodness of fit. All right, so first thing we're going to do is a chi-square test for differences in population proportions. Are these three true populations of Manhattan students, Bronx students, Dobbs Ferry students, are they different in the true population? You have some evidence that they are because your sample shows different sample proportions. But is that enough evidence for you to say that that applies to the whole population? We already have one measure, or two measures, of answering this question. The first, we learned a month or so ago, proportion confidence intervals. So we could look at this 89% of Manhattan students, that's a sample proportion, and we could build a confidence interval. And you would say, I'm 95% confident that the true population proportion of Manhattan MBA students is between 84 and 97. You could do the same thing here, same thing here. And if those confidence intervals, all three overlap, what might you be led to possibly believe? They're all the same. All right, the true population proportions are all the same because your confidence intervals all overlap. All right, so that's one way you could solve this problem. A slight variation is you could use proportion difference confidence intervals. Chi-squared is just a different, more concise way to do that. Chi-square is a common test among statisticians. Has anyone ever heard someone present findings and said, I did a chi-square test? Has anyone heard that? Okay. So it makes you sound a little impressive, right? When you say I did a chi-square test. It does.
I think I heard that on the news.
Okay. You're gonna know.
The little servers in this channel, the other channel, the other channel, and then they claim that the whole server is fake and whatever and whatsoever.
And, okay, and they said they did a chi-square test and they found that it wasn't fake or something like that?
Well, probably it wasn't fully understanding the concept, but probably I heard the word.
Okay, good, Good, so you, at the end of tonight, you will know how to use a chi-square test, how to interpret a chi-square test. It's people who don't understand statistics won't know what it is, but people who understand statistics, you'll be able to talk more concisely with them. Talk in shorthand. Say it to your son, fantastic. The thing about giving confidence intervals is sometimes it has a difficult effect. If you say the confidence interval for the true population proportion, by the time you get done saying that, you've said a lot. So people are looking at you like, what is this? I don't understand. You kind of think you know something, but it doesn't sound like it's that difficult. So at the same time they hear you say this, they may think that they know how to interpret just based on what you said. So sometimes you can be slick about it and say, well, I just did a chi-square test, and leave it at that. In any case, you will now have another tool, chi-square test, to answer this question. All right, our null hypothesis for this test will be, can someone read the null hypothesis to me? What's this little symbol mean? Population proportion 1 equals population proportion 2 equals population proportion 2. The true population proportions are all the same. That's our null hypothesis. A null hypothesis we will believe unless we have overwhelming evidence to the contrary. If we do, we will reject the null hypothesis and assume the alternative. The alternative is simply that not all the population proportions are the same. One of these is different. It's either Manhattan, Dobbs Ferry, or the Bronx. They're all three different, but at least one is different. All right, so rejecting the null hypothesis in this case means that, what does that say? Can someone read the rest of that too on your slides?
That at
Means
least,
that at least one of the population proportions is different from the other.
Okay,
Sorry.
good, thank you. All right, so let's do it this way. So here are our results. When you do a chi-square test, you want to put it in a table where you have all of the options. So you ask the students, do you think you have adequate course offerings? Yes. The other option was no. If you had a maybe, sometimes option, you could include that as a category. But we'll keep it simple, just two options. And you had three categories, three populations of students. You're going to put the raw numbers, the actual numbers, people who said yes, no. You're going to put the totals. And then the next question you're going to think about is you're going to say, if the null hypothesis is true, what would I have expected for each of these cells? So this is the observed frequency in your sample, these numbers. Next question. If the null hypothesis is true, what would I expect of these frequencies?
to be the same, to be the exact.
Then the denominator?
Yeah, the exact same. We're on to something. So, of the total 300 students who were surveyed, how many said yes? 227.
Total.
Out of 300. What percentage of total students said yes?
Does 227 divided by 100?
By 300.
300, excuse me.
70, roughly 75%?
76.
76%? Alright, so if the null hypothesis is true, and the true population proportion for all three of these is the same, then we would expect 75% of respondents to say yes. So if we asked 100 people in Manhattan, what percentage of respondents, or how many of them would have said yes?
Just Manhattan alone, right?
Percentage.
What you said?
Let me get the right number.
So in Manhattan, how many students would we have expected to say yes? We asked 100, how many would we expect to say yes if the null hypothesis is true?
At least 75.
So can you be more specific, more exact?
75.
76, is that 75, 66?
75.6, let's go with that. 75.6 students would have said yes. That would be our expected frequency. Now keep that exact number. Divide those students in half. How many would we have expected to say no if the null hypothesis is true? Let's do it the same way. How many people total said no?
73.
73. How many people did we ask total?
300.
What percentage of students said no?
24%.
24 and change. If we asked 100, how many would we expect to say no?
24.4.
24.4. Very good. All right, let's do the same thing for this cell. How many students would we have expected to say yes in Dobbs-Ferry if the null hypothesis, all three true population proportions are the same, is true?
75.6.
75.6. How about Bronx?
75.6.
75.6. Fantastic. How many would we expect to say no in Dobbs-Ferry? 24.4. 24.4. All right, good. So now we have a table with all the possible outcomes for all of our categories. We have the observed frequencies and we have the expected frequencies. So when we initially looked at these numbers, we said, well, they're different from each other. But the question is, are they different enough that we can say the true population proportions
No,
are completely different?
no, it's not different enough. They are the same.
Okay, so maybe it is, maybe it isn't. We want a way to quantify it. So we're going to quantify the difference between these two, the difference between these two, the difference between these two, the difference between these two. We're going to add that up somehow. And we're going to say, is that total difference, is that so different, is that enough for us to reject the null hypothesis?
Oh, no, I sort of answered my question. I was gonna say that probably we could compare Manhattan and the Bronx, which have a bigger difference, but you're comparing it actually to the average, so.
Yeah, so if our null hypothesis, what's our null hypothesis one more time, Adonis? Yeah. Null hypothesis, the true population proportions are all the same. All right, we have some evidence that that's not true. We have sample evidence that looks like they're different. But we wouldn't expect our sample to be exactly like the true population all the time. That would be weird, right? If every time we took a random sample, it was exactly the same as the true population proportion, that'd be weird. So we'd expect some difference before we could say, you know, if the true population proportions are different. The question is this enough difference? So we have a way of adding it up. We'll call it the chi-squared test statistic. For each cell, we will take the observed frequency minus the expected frequency. We don't care so much if it's positive or negative, and also statisticians like to square things, so we will square that difference. Especially statisticians like to square differences. I think it's helpful for calculus somehow. I don't remember. And we will divide by the expected frequency. So observed minus expected squared, divide by expected. So let me write that up again. Can someone, so let's do observed and no. Let's do, no, we want the test, we want the results here. So for each of these cells, I want to take observed minus expected squared divided by expected. Okay, so let's break up and do that. Should we do that? All right, so Dina and Wendy, can you do this cell? Monica, Roxanne, and Nick, can you do this cell? Tina, Eileen, and Keisha, can you do this cell? Adamson, Kelsey, can you do this cell? Christina, Tang, Chris, can you do this cell? Amanda and Darlin, can you do this cell?
75.6. So Professor, let me just ask, the two sigmas in front, Do we need them? Are they part of the equation?
It's not supposed to be this.
I'm not using it.
Oh, yes, use the
So
exact.
basically observed,
Observe is, are we doing 100 for that location or entire?
observed frequencies, wouldn't it be the 77? No.
The big E signs, that just means we're gonna add them all together.
Oh, is that it? Okay, so the observed would be 77 minus 75.6. Square that and then divide that over the 75.6. That's it?
Because the 75.6 we actually showed.
That's the expected.
Gotcha.
So it's observed minus expected, square that, divided by the expected. So the 77 what we saw, what we actually saw, minus what we expected, which is 75.6. We're gonna square that. After we square that, well, after we subtract, we square that, and we divide that with what we expected, which is 75.6.
What's the difference between expected and predicted?
The same? I guess they're the same? Yeah, expected, predicted might be the same. Our difference is observed.
Right, no, I know, yeah.
Yeah, I have that one. The previous quarters, I just decided not to. Yeah, I saw it. I gave, don't worry, you'll get credit, that's and I give you an extra credit for it. So
That
yeah,
is
credit.
0.02.
You went above and beyond.
We got 0.0259.
What do you got, Roxanne? For which one?
Zero for Dobbs Ferry, yes, 0.0259. I mean, how far do you want us to go, Picasso?
No, that's good enough.
That's good?
Yep. Anyone else?
For
The results coming in?
Manhattan students, yes, 2.375.
2.375.
If that's all we have.
Where are you? Bronx students, yes? 2 point what? 819.
Easiest thing on the last class.
I don't know. Yes.
Dobbs Ferry, no, we got 0.07.
0.0 what? 0.08?
Same thing in
Okay.
total, but I'm going to.
Well, they are all calculated. Split us up by cells.
No, but I mean, it's still the same formula.
So I guess for this, now, this
Calculate, no, it's just.
would be the same formula, but the thing is that what exactly are we calculating here? What is this formula for?
3, 6. All right.
Is this the chi-square
Good.
test?
So we now have a quantifiable way of expressing the difference between what we observed and what we would expect if the null hypothesis is true. We did this for each cell, and we're now going to add all of these up. Can someone add these 6 up for us? You can give me a rough estimate.
16
So 9.645 for the first row across.
Just the total of all 6.
Oh, you want everything?
All 6 added up.
21.3.
21.31?
Yeah, I'm rounding.
I like it. I think that sounds right. So here are the numbers. Those all look right? Yeah, the numbers, the actual numbers I calculated on the next slide. Looks like we got them all right. And we add all of this up. And we compare that. They're right?
The numbers that you have.
They're a little off because we rounded off.
Yeah, they look pretty good. They look pretty good. Alright, so here's the thing.
So it's 21.
We got a quantifiable amount of difference. And we're gonna look at that difference on a chi-square frequency distribution. This is a chi-square frequency distribution. So this is the frequency or probability. This is the outcome of a chi-square test statistic. You all just calculated a chi-square test statistic of 21.3 something. Where would your chi-square test statistic fall on the frequency distribution? That's the question we're going to ask in a minute. Let's take a look at this frequency distribution. Would we expect a chi-square test statistic of 0? Well, that would mean that our sample is exactly the same as the true population proportion. Again, we said that would be weird. So we're going to have some difference in our sample. So you can see the highest point on the chi-square frequency distribution is somewhere above 0. We would expect some variation. But if it gets so much different than 0, and so far away from where we would expect that difference, that variation to fall, then we're going to get to something that is unlikely, an unlikely outcome if the null hypothesis is really true. If our chi-square test statistic falls in this upper tail, that is a sample outcome that is unlikely if our null hypothesis is actually true. And again, what's our null hypothesis?
They're all equal.
All three true population proportions are the same, Manhattan, Dobbs Ferry, the Bronx. If we find so much difference in our sample, we're going to start to think about rejecting that null hypothesis. We're going to find some difference, that's fine. But so much difference, then we start thinking about rejecting the null hypothesis. So you all found a chi-square test statistic of 21.43. You're going to need to look in the chi-square table in the back of your book. And the chi-square table has to do with how many different categories we had, how many different possible answers we had. If we have more categories, more possible answers, we would expect more difference. So we're going to quantify that with degrees of freedom. Chi-square degrees of freedom, rows minus 1 times columns minus 1. I think I may have skipped over that somewhere, right? Did I?
At the bottom of the distribution.
Oh, okay, bottom of the distribution, all right, you all have to be sharp here. I just love writing on the board for these slides, but hopefully you don't miss anything that's on the actual silver part. So the degrees of freedom for a chi-square frequency distribution, rows minus 1 times columns minus 1. So we have 3 rows, Manhattan, Dobbs Ferry, Bronx, and we have 2 columns, yes, no. So 3 minus 1 is 2, 2 minus 1 is 2, 2 minus 1 is 1, 2 times 1 is 2. Degrees of freedom is 2. So, if you're looking at a 5% significance level, you're going to flip to the back of the book, the chi-square distribution. You're going to look for 2 degrees of freedom. Now the chi-square has a whole separate table for 5% significance level. Or, no, it doesn't, never mind, it doesn't. I'm thinking of a different distribution. So look for 2 degrees of freedom, and if our significance level is 5%, this is a little different than we're used to, but that entire 5% is going to be in the upper tail. This is not where we will split the significance level and make it a 2-tailed test. The whole 5% is going to be in the upper tail. Because that's the only unusual part of the frequency distribution.
Of this specific example or of all?
All
Chi-square.
chi-square tests. Like, it would be weird if we had 0 variation, but still that wouldn't, it would be like, alright, I got exactly what the population proportion is supposed to be. So that would be a little weird, but that wouldn't be a reason to reject the null hypothesis. The only reason to reject the null hypothesis is if we have a whole lot of difference in our sample compared to what we would expect. Okay, so everybody got the chi-squared table open, 5% with 2 degrees of freedom. How much area is in the upper tail? 5%. What is the critical value? 5 point what? 5.991. Yes. So the critical value, this, is 5.991. What was our test, our sample statistic? Now known as our chi-squared test statistic. 21 and change. 21.14 something. That's way out here. What is our decision? Reject. We reject the null hypothesis. The null hypothesis that all of these population proportions are the same, we reject that because we found so much difference in our sample. Okay, any questions? Yes, Monica.
Can you just go over the
They said the 5%.
degrees of freedom again?
Yeah, so the degrees of freedom, if we have more categories or more possible outcomes, we're going to expect more difference between our sample and the true population proportion under the null hypothesis. So more categories, more outcomes would mean more difference would be likely. So the way chi-square calculates that, rows minus 1 times columns minus 1 is our degrees of freedom.
Okay.
Times columns. So if we have a whole bunch of rows, a whole bunch of columns, then we're going to expect the chi-square statistic to be a little bigger. And our cutoff point for something unusual would also be a little bit bigger. Any other questions on that? All right. So now you remember the good news on the chi-square test for independence? It's the same thing. So I want to ask you this question right now. Is opinion and location, are they independent?
For this example,
This example.
no.
No. Why do you say no?
And they're not independent because I believe that because we rejected the null hypothesis,
Yes. And what would the null hypothesis say?
that differences were the same.
Yeah, so we found that the true population proportions are different. Manhattan, Dobbs Ferry, the Bronx. The actual proportions of people who say they like the class offerings or approve enough class offerings, that's different. So your opinion now depends on which location you reside. So these two factors are not independent, they are dependent. They're dependent. Opinion depends on location. You all have proved it.
We did it.
Yes. Mission accomplished. Now you probably knew that before you even started the question, right? Manhattan students have a different opinion than Bronx students.
Right.
Now you have proved it statistically. Good job.
Thanks.
Yeah. So you have answered this question, but we'll just talk for a couple minutes about how we would set this up. The really only difference would be that null and alternative hypothesis and the way you would interpret it, the way you would talk about it. So chi-square test for independence. This is the same thing we did with regression analysis. We tried to figure out is there a dependence among two variables? All right, if we graph study time, will we see an upward slope on your grade? That means that they are dependent on each other. If it was just a straight line, they would be completely independent. So we could do this with regression analysis. We could do confidence intervals for proportions or proportion differences. just like we did in the previous example. We could say, well, if the proportions are different in the true population, then in fact they're dependent on each other. Null hypothesis, the factors are independent. No relationship, straight line. Doesn't matter which place is your main campus, you're going to have the same opinion. The alternative is that the factors are not independent. They are. Location is, or opinion is dependent on location. So what is our decision going to be ultimately? Are we going to reject this or fail to reject this? Reject this. We're going to reject this because we have sample data that says, in fact, they are not independent. And the sample data is so compelling, it is very unlikely if the true population, if the factors are independent in the true population. Remember our cutoff point for what we would be willing to believe was 5.9, and we got 21.3. Okay, we found overwhelming evidence to the contrary. You say these factors are independent of each other. I have overwhelming evidence to the contrary. In fact, what do you think the p-value of this chi-squared test statistic is? The p-value.
Very small.
What's that?
Very small.
Yeah, anybody want to take a guess? Just take a guess, just throw it out there. What do you think the p-value is? A bazillion zeros and then some number? Okay, yeah, some bazillion zeros and then some number. So again, the p-value is the the p-value is the probability of this sample outcome if the null hypothesis is true. We know it's less than 5% because this is the 5% cutoff. Now we're in like 4%, 3%, 2%. Now we're into some tiny, tiny percentage. 1,000th of 1%. That would be the probability of this outcome if these factors were truly independent. Yes? Okay, feel better. You can watch the video. And it's up to you. We've all had our shots, right? All right, great. So we've now done the chi-square test for proportion differences and the chi-square test for independence. We found there's some very similar methods of calculating both of them. Last I mentioned, we'll just talk about the chi-square goodness of fit test. So the chi-square goodness of fit test, if I want to be more specific than saying they're just different in the true population, or they're not independent, or they're dependent, if I want to say I actually think the true population proportion of Manhattan students is this amount, Bronx students is this amount, Dobbs Ferry students is this amount, okay? It's going to be unlikely that my sample of 100 students is going to be that exact number. So I'm going to have some difference. Question is it really different from what I assume it is? If it's really different, then what do you think I'm going to do to this null hypothesis? Reject it. All right, if my sample data is really different from this null hypothesis, then I will reject it. And you'll calculate the chi-square test statistic roughly the same way. There's just a couple of tiny differences, and I don't think you need to bother with them. So process would all be the same. But you now know chi-square goodness of fit test. I think you can talk to it. You know how it would be set up. You know, someone's standing up there giving you a lecture. They said if they say I did a chi-square goodness of fit test, and it passed. They say it passed. Sometimes they'll say it passed the hypothesis test. These numbers could be true. Alright, so what I have now is just some slides filling out the chi-square content, and I've got 2 examples, one for each, proportion differences and independence. But you have it, you have all the content. You know what the chi-square test is, or in each case, you know how to calculate it. I've just got some slides filling that out, and we'll do one example for each. How are we doing on time?
725.
7:25? Alright, good. So, let's just review what we already know. Chi-squared, distribution made of the sums of normal deviance. Alright, how much does our sample deviate from the expected outcomes? The shape of the distribution will depend on degrees of freedom. How many categories, how many answers. If I have more of them, I would expect a little more difference. If I'm comparing my sample to the assumed null hypothesis, 0 difference would be weird. I'd expect some difference, but if I have so much difference, I'm rejecting the null hypothesis. Null hypothesis for differences in population proportions. As I say, in fact, the true population proportion of Manhattan students, Dobbs Ferry students, Bronx students is the same. Alternatively, they're not all the same. Summary of our procedure that we used. We showed the observed frequencies. We built a table of the expected frequencies. And you're always going to use raw numbers in these. We use actual numbers of students who said yes, actual numbers of students we would expect to say yes. Don't ever make the mistake of putting these into percentages. Use the actual numbers. Calculate the chi-squared value. We did that. We broke up into teams. We calculated the value for each cell. We added them all together. We applied the decision rule. If our chi-squared test statistic is greater than the chi-square critical value we find in the back of the book, this critical value is our cutoff point for highly unusual. If what we find is bigger than that, we reject the null hypothesis. We could also use the p-value version of making a decision. With a really, really low p-value, reject the null hypothesis. Yes?
How do we get the p-value again?
We would use Excel.
Okay,
Yeah. We just guessed.
okay.
Remember when I said 21, what do you think the p-value is? It's some really, really small number. It's definitely less than 5%. And it's probably really less than 5%. How do we calculate the expected frequencies? We just intuitively went through it in our example, but there's a little trick. Column total divided by grand total times row total. That's not worthy of worrying about, so let me just quickly go over that. So we want to know the expected frequency of Manhattan students who would say yes. So column total, how many students total said yes, divided by grand total, how many students we talked to, that's the percentage of students who said yes, times row total, which is the total number of students in Manhattan. So the trick is column total divided by row total times, column total divided by grand total times row total. And then the chi-squared test statistic, in each cell observed minus expected squared divided by expected. These sum signs, this just means sum all the rows, sum all the columns. Add them all up like we did, we broke up into 6 and we added that all together. Alright, an example. We work for Alvarez Communications. We've just received 3 shipments of cell phone shells, sort of these shells around cell phones. And we're going to assemble these cell phone shells. Each shipment is from a different supplier. Alright, now these shipments say they're really huge. Say we got 20,000 shells from each supplier. We're going to take a sample. We can't test all 20,000 shells from supplier 1, 2, and 3. So we're gonna take a simple random sample of 200 shells from each supplier, and we're gonna see how many defective